Welcome back, Leo Lions. This is Mrs. Morgan with today's lesson on rational and irrational numbers. So we're going to start out with two definitions. Rational numbers, to make it as simple as possible, rational numbers are any number that can be written as a fraction. So numbers that can be written as a fraction, or we can also write them as decimals. The way I remember this is in the word rational, we have the word ratio. A ratio is the exact same thing as a fraction. A ratio is something like 3 to 5, and then we could write that as 3/5. So that's a fraction. So rational numbers always think fractions, okay? Rational numbers do include two types of decimals. So terminating means that they will end. They end in a remainder of 0. They stop. And we don't have that little ... or a decimal that goes on and on forever. Terminating means stops. And repeating. So a number that repeats over and over, or a block of numbers, those are what we call repeating decimals. Also, the square roots of perfect squares are rational numbers. So for example, we talked about square roots already. If we do the square root of 49, rewrite that so you can see it. 7 times 7 equals 49. So the square root of 49 is 7. Well, we can write 7 as 7/1, so it's a rational number, okay? Irrational numbers are numbers that we cannot write as fractions, okay? Irrational numbers include, there's two types of decimals. So non-terminating, meaning they will never, ever end. They go on and on forever, but they cannot repeat because we already said repeating decimals are up here in the rational category. So non-terminating and non-repeating decimals are irrational numbers. All right. Also, the square roots of non-perfect squares. So there are lots and lots of irrational square roots. Something like the square root of, let's say, 7. We can't take any number times itself to equal 7, any whole number. So that's why this is going to turn into an irrational number. If you plug that into your calculator, it's going to go on and on forever, and nothing is going to repeat. Okay, so let's look at some examples. -12, always ask yourself, can you write it as a fraction? So -12/1, it works. So this is a rational number. All right, when we do our explanations over here, well, the reason for that is that it can be written as a fraction. Okay, next one, pi. That is one of the most common irrational numbers. Hopefully you guys know pi is, the value is 3.1415926, so on, so on, so on. It goes on and on forever. So nothing repeats, and it goes on forever, so it is irrational. All right, the explanation for that is it's non-terminating, meaning it doesn't end, and it is non-repeating, so we cannot write pi as a fraction. And I'm going to put down that is a non-terminating, non-repeating decimal. Okay, 0.6. Ask yourself, can we write it as a fraction? So we've been talking in class how to go fraction to decimals, so we know 0.6 is the same thing as 6/10. So that is rational because we can write it as a fraction. Okay, and I'm going to put here, it's a terminating decimal as my explanation. So terminating decimals we can always write as fractions. Okay, 7/8, well, it's already a fraction. So that one is rational because we can write as a fraction. All right, next one, 0.12345 is there a number or a group of numbers that are repeating? No, and it goes on and on forever, so this is irrational. All right, the same definition from up above, it is non-terminating, non-repeating decimal. All right, next one is a repeating decimal, so 0.333333, so on. Honestly, I think this is written wrong. We've talked about this. We should only write the 3 once. This is a common fraction, so if you don't know, 1/3 turns into a repeating decimal of 0.33333. So I showed you there, you can write it as a fraction, so that is a rational number. All right, I'm going to write down, we know all repeating decimals can be written as a fraction. All right, square root of 20. Does this come out to a perfect whole number? Does it come out to something times itself equals 20? It doesn't work, so that is a irrational number. Definition or explanation for that would be a non-perfect square. Something like 25, 5 times 5 equals 25. Well, that would be rational, okay? Negative 1.75, it ends, so we can write that as negative 1 75/100ths. So we can write it as a fraction. We know all terminating decimals can be turned into a fraction, so it's rational. So the reasoning, it's a terminating decimal. And last one, the negative square root of 121. So is that a perfect square root? What times itself gives us 121? Well, that would be 11. There's the negative sign out front. We can put it over 1. There we wrote it as a fraction. So that is a rational number. Okay, and we talked about all perfect square roots are going to be rational. Okay, so we got that list done. Let's look at some of these examples on the back side. Joseph wants to find the side length of a square that has an area of 150 feet. Should this answer be rational or irrational? So if we have a square, remember a square has same side lengths. We know that the area, everything inside here, is 150. And it should say square feet. And to find the side length, well, we would take the square root of 150 to find what times itself gives us 150. Is that a perfect square root? It is not. So this is an example of an irrational number. And why? This is a non-perfect square. All right, next example, which value from the following list of numbers is not a rational number? Well, this terminates, so that one we could write as 8 224 thousandths, so that is rational. Fraction already, 5/9, so we're good there. The square root of 25 is 5, so that is rational. A repeating decimal, we can write that as 321 over 999, so that's rational. And then square root of 30 is not a perfect square, so that one is not a rational number, and that's because it is not a perfect square. All right. Brad converted 5/11ths to a decimal, and his result was a repeating decimal. Does this mean that the value is rational or irrational? This means that it's rational. We already talked about repeating decimals are always rational. So first of all, 5/11ths is a fraction. So we know 5/11ths is rational. And then when we turn it to our repeating decimal, it's the same thing. The repeating decimal is the same number. So repeating decimals can be written as fractions, okay? Next one, 3.4567. It doesn't have the dot, 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 so it terminates. That is a rational number. 3.4567, here is the dot, dot, dot. It shows it goes on and on forever. Nothing repeats, so that is irrational. 3.456, and then look above the 7, there is the repeating. Even though it's not all of it repeating, just that 7 repeats, any sort of repeating, it will be rational. Okay? Next one, the square roots of 30. This is not a perfect square, so if we took that square root and then added 6 to it, it's still going to be irrational. So anything with a non-perfect square root is going to be irrational. Now here, the b, we would add first. So 6 plus 30 is 36. Now is 36 a perfect square? It is. 6 times 6. So that one is rational. However, this last one, we can't add them because they're separate. You'd want to take the square root of 6, the square root of 30, then add them together. Well, both of those are non-perfect square roots. They don't come out to perfect whole numbers. So this is going to be an irrational answer. Okay? Last one, just give an example of an irrational number that is greater than 10. There's so many different answers for this. I'm going to write down just a random one. What if we did 20.43443? I've seen this example before. 4443, and I'm going to put those little dots. This is showing that it goes on and on forever. There is a pattern, however, there's not a certain number or numbers that repeat over and over. So this is an example of an irrational number. All right. Thank you guys for listening. That concludes your lesson on rational